Okay, let's discuss energy in a magnetic field. And now remember, when you're studying circuits, it's very, very handy to think of circuits in terms of energy. If you have a battery takes chemical potential energy and adds energy to the circuit. And so all the little charge carriers up here and the top of the battery are going to have more energy per unit charge than down here. So this is the supply of energy to the circuit. Okay, and we give it an EMF or a delta V, a voltage. Then we have then we studied capacitors. And capacitors gave us a voltage drop. If you went with like if you had positive charge here and negative charge here, that created an electric field inside there. And therefore we had a voltage drop, and that was equal to the charge on here divided by the capacitance. Now we have inductors. And we said that the voltage drop due to an inductor, well, that depends on if you're changing the current. And now, if the current's constant, you got no voltage drop. But if you do have a changing current, then you're going to have a voltage drop. And this creates, when it has current flowing through it, this creates a magnetic field. Now remember, magnetic fields come in loops. Okay. And so from an energy point of view, this contributes energy. This stores energy in an electric field. This is going to do the same thing. An inductor is going to store energy in your circuit. And an electrical engineer can use that fact to design circuits to do all kinds of wonderful things. But you have to learn the basics first, the basic physics first. Of course, we had resistors, and we'll talk about resistors here in a little bit. We're going to focus on this. So, if I have an RL circuit, let's draw it here. Oh, just to be complete, let me just add a resistor over here. Here our delta V is equal to I times R, and here we get a voltage drop because energy leaves the circuit doing work or heating something up. Energy leaves the circuit depending on how much current is going through it. Okay, now let's go to an RL circuit, so here's the R and here's the L. And when I take a switch and I close the switch, I get a rush of current through it. And we said that, well, I've got this guy here. This is the energy per unit charge that's being added to the circuit, minus, we got a voltage drop here because I've got current running through a resistor. Energy's leaving the circuit here. But then we have this minus L di dt. And this is the voltage drop that I get because I'm changing the amount of current flowing through it. Now, eventually, if I leave this on for a long time, this is going to, the voltage drop due to the inductor is going to be zero because the current is going to reach its steady maximum current. You wait 5 tau or something, right? But immediately after you close the circuit, well, there is no current yet, so all the voltage drop is across the inductor on that first instant in time, and then it's a combination of the two is equal to 0. Okay, well, what I want to do is figure out how much energy I'm storing in this inductor. I want an expression for the energy. Well, and I'm going to do it in a very clever way. I'm going to take this equation, and this is the voltage man equation, right? We got voltage increase, voltage drop. I'm back to where I started. I'm going to take this equation and I'm going to multiply it by the current at some time t. Just multiply the whole thing by I, and I get IE minus I squared R minus IL di dt, right? Now, let's think about what this is. What is voltage times current? Do you remember what that is? It's watts. It's measured in watts. It's power. So what this tells me is the rate at which the battery adds energy to the circuit. Joules per second. And what is this telling me? Well, this tells me the rate at which energy is leaving the circuit through the resistor. So what does this tell me?
The rate at which energy is stored.
The rate at which we are storing energy in the inductor. Okay? So,
sorry.
what's, oh, yes? Can I repeat that?
Yes, please.
Okay. So, think about this in terms of energy now. Okay, this is a conservation of energy. This is voltage man saying the voltage increases have to equal the voltage drops. So I get this equation. And then I just use little rules of algebra. Hey, multiply everything by I, and it's still going to be equal, which is cool. And so I multiplied each one of these by the current. Now, if I multiplied the voltage of the battery by the current flowing through the battery, this is the rate at which energy is being added to the circuit. It's the power of the battery. So this is the rate at which energy leaves the circuit, I squared R. Remember, P equals I squared R for a resistor. Which means that this is the rate at which we're adding energy to the circuit, storing it in the magnetic field of this inductor. So what this is it's the rate ddt of how much energy is being stored in the inductor. Well, what symbol do we use to represent stored energy?
U.
Capital U. So I'm going to call this U sub L, the energy stored in the inductor. And this is equal to, it's going to be equal to this, which is Li di dt. So what we have here is du dt is equal to Li di dt. The rate at which I'm storing energy in the inductor is equal to this expression. Well, I just cancel out the dt's. So this means that du, the rate at which I add energy to the inductor, it's not a rate anymore, a little tiny bit, thank you, let me zoom out. A little tiny bit of energy added to the inductor is going to be equal to L times I di and so now what I want to do is integrate both sides. And this is going to be from, let's say at time t equals 0, there is no current, there's nothing. And then like some initial U, which will be, and this is final U, but this is going to be 0. So U final minus U initial, right? That's what this turns into. Well, you guys, this is pretty easy to integrate, isn't it? Now let's suppose that the initial current is 0, and this is going to be whatever our current is at some time t. And so this becomes L. Well, what's the integral of I di? Yeah, it's I squared over 2, going from 0 to I. And so our change in potential energy, or the potential energy in the inductor, which we'll just call U, we'll just say the initial is 0, is equal to 1/2 L I squared. And this is the equation for how much energy is stored in the inductor because there's current, because there's a magnetic field. Okay, now I want you to think about this. If I've got current flowing in that inductor, that means that inductor, which is just a solenoid really, it's got a pretty intense magnetic field. And it took work to make that magnetic field. I mean, you had to put energy into it to get that magnetic field to happen. I mean, it just doesn't happen on its own. Whenever you make change to the universe, it took energy to make that happen. What's the change here? When I closed this switch, I created a magnetic field. I changed the universe a little bit. It took energy to do it. How much? This much. Okay? Now, we're going to use this to figure out something very interesting. In other words, we're going to see that if you have a magnetic field, there is just energy stored in that magnetic field. Now, we did the same sort of thing with electric fields. But now we're going to do it for magnetic fields. If I have a solenoid, it was shown in one of the examples in your book, and I'm not going to rederive it now because I don't have time, that the inductance for that solenoid is equal to mu naught times n squared times the cross-sectional area of that solenoid times the length. Well, now the area times the length, that's really the volume of the solenoid. So this was derived in one of the examples that you were assigned to do. Now, if you haven't done that yet, which I don't expect you to have because we just did it yesterday, but if you did, great. If you didn't, just accept this. You're going to go through the example. This is the inductance of a solenoid based on the characteristics of that solenoid. And what are the characteristics of a solenoid? How long it is, what its cross-sectional area is, and how many turns of wire per unit length you have. Okay? Now, I'm going to say, well, if I've got a certain current I flowing through here, the energy stored in that solenoid is going to be, there's one, it's going to be 1/2 L, 1/2 L I squared, but we know what L is, right? We know that L is mu naught n squared A times L. But there's one other thing I want to express this in terms of the magnetic field inside. So what do we know is true about the magnetic field inside an inductor? What's the B field? What's the strength of the B field in there? Remember we said that B inside is equal to mu naught N times I. Okay, well, what I can do now is solve for I. I is equal to B over mu naught times the number of turns per unit length. And now I'm going to substitute this into this equation here, and so this is going to be B squared over mu naught squared N squared. So this is the energy, the equation for the energy of an inductor 1/2 Li squared. But we're doing it specifically for a solenoid. So we substituted for the inductance of the solenoid, and we substituted for the current in the solenoid in terms of the magnetic field, mu naught, and the number of turns per unit length. Well, now I just need to clean this up, and a lot of it does clean up. You got 1/2 still, but you got a mu naught canceling with the mu naught squared. We have an n squared that goes away, and then we have a b squared over mu naught, and then we have this a times L. Okay, A times L, that's left. So there's my expression. This is the energy stored in a solenoid in terms of the characteristics of the solenoid. And notice that it really only depends on the strength of the magnetic field in there and the volume, which makes sense. But what I really want is an expression of energy per unit volume, which I'm going to call little u. And we did this before. I'm going to call it sub b because we did this for electric fields. Is equal to the energy stored divided by AL, right? What is this? Joules per cubic meter. That's the energy per unit volume is equal to 1/2 b squared over mu naught. And this is the energy stored in a magnetic field itself. Notice that when I express it in terms of energy per unit volume, I no longer have the characteristics of the solenoid. I just use the solenoid as a way of getting this. This tells me that if I have a magnetic field that in a volume of space, there is energy stored in that space itself because there is a magnetic field there. And that energy, we can figure out that the energy per unit volume is just b squared over 2 mu naught. Now we did this before. Whoops. We did this with electric fields. The energy per unit volume for an electric field was 1/2 epsilon naught times E squared. So it's very similar. It's just that you have a mu naught on the bottom, and here the epsilon naught was at the top. So these are two equations that are... Now, I wouldn't say these are the biggest, most important equations that you need to know to get ready for the AP test. But it turns out that these are super profound ideas in upper level physics. And if you're going to study more physics, at the upper division level and beyond, these ideas of energy stored in a magnetic field just in, per unit volume of space, it turns out to be a very, very important idea. And it leads to really, great things like relativity and stuff like that. Okay. So that, let me zoom all the way out. I'll summarize here. So think about a circuit in terms of energy. That's always a great way to deal with it. Batteries add energy. Resistors take energy away. Inductors and capacitors store energy. Capacitors store energy in an electric field. Inductors store energy in a magnetic field. And so we can also say, or we derived an expression for how much energy is stored in an inductor because it has current flowing through it. That's right, this expression right here, 1/2 Li squared. And then we can use the characteristics of a solenoid to derive an expression for how much energy is stored per unit volume in just space because there's a magnetic field there. And then recall that we did the same thing for electric fields. But this is, that's as far as it'll go. This is really, profound stuff. And you can use it to solve a few problems too.